Hi folks, we're going to take a look at the solution to number 17 on page 112. So they give us this function here which represents the number of items that can be scanned per minute by a cashier after they've worked for T hours. Okay, so the first thing they want us to do is to find the derivative of the function, and then in B they ask us, does the cashier ever stop improving? Okay, so let's start by finding the derivative of this function. Now you may not need to, but it might be a good idea to rewrite the function in a more user-friendly form for taking the derivative. Okay, so what I mean by that is taking this square root of 9 plus t squared that's in the denominator, bring it up into the numerator, and use an exponent instead of a square root. So I'll write that as 20 minus 30 times 9 plus t squared to the negative 1/2. Okay. It might just be a little easier to see how the chain rule is going to be used. Okay, so I'll find the derivative here. So derivative of 20 is just 0, so that's going to disappear. And here I've got this negative 30. So by the way, don't forget that there's still a negative. Even though the derivative of this is 0, people often forget this negative in front of the 30 is just a constant times a function. Okay, so we can just write that as the constant times the derivative of the function itself here. Okay, so to find the derivative of this function, well, we're going to have to use a chain rule. So this is going to be our u here. So first we take the derivative of u to the negative 1/2, which is just negative 1/2 times u to the negative 3/2. And then we have to multiply that. So that's the derivative of the outside function. And now we have to take the derivative of the inside function and multiply. So derivative of 9 plus t squared is just 2t. Okay. Now, it would be fine to leave it that way if I was just asking for the derivative, but since I'm going to likely use the derivative in B, I'm going to clean this up a little. So here we have the 2's that reduce. I've got these negative signs that become positive, and so what I'm left with in the numerator is just the 30 and the t. Okay, and in the denominator, I'm going to bring this down to the denominator because of the negative exponent. So I just have, so first I'll cube it, 9 plus t squared cubed. Okay, and then the 1/2 is just going to represent a square root. Okay, so this is the derivative function, okay, the rate of change of this function n, which represents number of items per minute. Okay, so now let's talk about B. So does the cashier ever stop improving? Okay, well, let's take a look at the derivative. So remember what the derivative represents. It's the rate of change of this function here. Okay, and one thing I notice about this function is that n prime at t is always bigger than 0 if t is bigger than 0. Okay, so notice here, does the cashier ever stop improving? Okay, you should be thinking over time, in the long run, sort of even as the end behavior. And I notice that as t gets larger and larger and larger, so I'm not even necessarily interested in t equals 0, and I'm certainly not interested in any negative time values. Okay, so I'm only really interested in time values greater than 0, and I see that the derivative is always going to be greater than 0 because the denominator is positive, and I'm multiplying 30 by some positive number. Okay, so what does it tell me? It tells me that any time t, the rate of change is always positive. Okay, meaning the n is increasing at that particular value. Okay, so here our n prime at t being greater than 0 means at any time t, the rate of change is positive. So the tangent is increasing. Okay, so getting better and better and better. Now, they don't actually ask this question, but if we take a look at the long run, what do we notice about how this increase itself is changing? And I notice that as t gets really, really large, well, the numerator here has an exponent, a power of t to the 1. And if I look at the denominator, well, what does this act like? Here we have a t squared, which is going to get cubed. Okay, remember in the long run, this 9 is not going to make any difference. So that's t to the 6th, and I'm taking the square root of that. So t to the 6th to the 1/2. So in the denominator, this is going to start acting like t cubed. Okay, and if I have a t divided by t cubed, the denominator takes over. Eventually this derivative is approaching 0. Okay, so while the rate of change is always positive, the rate of change is also going to be approaching zero. So over time, this cashier is going to keep getting better, but by less and less and less. Okay, and so that's a reasoning as to why it's always going to be increased, because that derivative is always positive. Now, real quick, I think I could have answered this question just by looking at the function itself. Okay, because let's see if we can figure out the behavior of this function. Well, when t equals 0, so when this person first starts out, let's stick t equals 0. You got 9 plus 0 is 9, so square root of 9 is 3. 30 divided by 3 is 10. 20 minus 10. So at the very beginning, this person can scan 10 items per minute. But here, this 20 never changes. The only thing that's changing is the number that I'm subtracting. And notice that as t gets bigger, the denominator gets bigger, and so this whole number becomes smaller. So over time, I'm subtracting a smaller and smaller number. Okay, so it makes sense that over time, n is going to be getting larger and larger and larger. Okay, and if you notice, as t gets really, really large, this whole thing is going to be approaching 0. So this cashier is going to be approaching over time 20 items per minute. Okay, but always getting bigger. So we could have made an argument with respect to the original function also. Okay, so that's it for this one.